the idea for problem number, for the third example, which was example C, was to use the central limit theorem. Essentially what happens here is that we have 120 workers, which means that my sample size is 120, which is larger than or equal to 30. And that means that we can use the central limit theorem. And in particular, it tells us that we can use the third formula that we have in our table. Okay. In addition to that, we were told that the mean, where am I, was 16.2, and the standard deviation was 3.6. All right. By using the third formula, we had to simply evaluate x bar plus or minus z alpha over 2 times s over square root of n, which in this case means we're going to have 16.2 plus or minus 1.645, because this is the same value for z that we found last time. It's the value that separates the top 5% from the bottom 95%, times 3.6 over square root of n, which is square root of 120. All right, and if you did this, you should have found the interval 15.66 to 16.74. All right, could I see a yes for everybody that found this answer? And if I were to interpret this interval, and remember, you have to be very careful about how you interpret this type of intervals, what you would get is that we are 90% confident that this interval contains the true mean. And the true mean what? Well, the true mean of what we're looking at here, which is the mean time to assemble a new electronic component, right? So the true mean time required to assemble a new electronic component. Okay. And then for, what is it? For D, we have that the SAT scores are designed to have a distribution that is normal with a standard deviation of 150. That means a couple of things. It means that first, we are given the standard deviation of the whole population, because all of the SAT scores are designed to have a standard deviation of 150. And in addition to that, we know that this distribution is normal. Okay. In this case, we're trying to look at a sample of 27 randomly chosen test takers. Okay, so that means my sample is of size 27. And the average that they get is 1,103. And so what we're trying to estimate here is the mean for the SAT scores, right? So we don't know what the mean for the SAT scores is yet. All that we know is that they are designed to have a standard deviation of 150. And now we're going to see what the mean, like what our estimation for the mean is going to be, right? So that means mu is going to be the mean SAT score, which means that in this case, because we know that the distribution is normal, And because we know what the standard deviation of the original population is, we're going to have to use the first formula, which tells me that this is x bar plus or minus z alpha over 2 times sigma, which is known in this case, divided by square root of 27. All right, and if you do this, you're going to find the interval. I put the integers only, so I got 1056 to 1150. So I rounded to the nearest integer just because SATs are integer numbers, but it doesn't really matter. If you put a couple digits after the comma, that's fine. Okay. If I don't specify, then you're free to do anything. Usually I'll try to specify on a test how many decimals after the comma I expect. And once again, this means that we are 90% confident that the mean SAT score is between 1056 and 1150. Okay, so we are 90% confident that the mean SAT score is between 1056 and 1150. And once again, here you need to make sure that you understand what that confidence means. And the confidence just essentially, it just means that if you were to, like, this type of interval is designed so that if you take many samples of the same size and you compute an interval for each one of them, then 90% of those intervals are going to contain the true parameter, right? Now that means that for this one sample that you computed it, you don't know whether you fell in the 90% of intervals that contain the true parameter, or if you fell in the other 10% of intervals that do not contain it, but you have reason to believe, so you're 90% confident that you're going to be in one of those cases where the interval did contain the true parameter. All right, Vishaka, you have a question.
Yeah, can you scroll up a bit, please? Oh, okay. So in like question C, the parameter mu is like the time required to assemble.
Exactly. Yeah, I didn't specify time required to assemble the new component, like this one.
Thank you.
Could I see a yes for everybody that got this answer, please? Okay. All right, so as I said, what we're going to do today is then just introduce the concept and the logic behind the next statistical tool that we're learning, which is hypothesis testing. And afterward, if we have some time, I'll just give you some time to work on the practice set or the homework set number 8. We're going to see if we have time, so it'll depend on that. But for now, I want to start this section, which is just kind of the culmination of why we do, sampling distributions, why we had to talk about probability, and how we use that in order to draw conclusions from a given sample. Okay, so essentially this is the part where we learn how it is possible for me to conclude something about a population by just looking at a sample. All right. So I'm going to start with a little blurb. First, hypothesis testing. Hypothesis testing. So maybe I'll create like this margin over here because I'm going to then comment on everything that we did. And we're going to have this. Suppose that it is known that in 2015, the mean weight of a Canadian man was 177 pounds. Okay. Then there's a public health official. So somebody that works in public health official, believes that over the last 5 years, believes that in the last 5 years, the average has increased. The average weight of Canadian men has increased. Okay, this average has increased. Okay. So in order to verify whether this is the case, of course, she can't just decide that this is the case and claim that it is the case. Instead, she's going to draw a sample. She's going to compute the mean for that sample. And then she's going to try to compare it to the average that she had for 2015, right? And the sample that she selects, she can't just weight all the Canadians. She's going to have to select the sample. It's going to have to be a finite amount, a finite number of Canadians that she's going to look at. And from them, she's going to compute an average, and she's going to try to make conclusions about all the Canadian population in 2020. All right. So that's kind of the idea here. We want to generalize something that that we observe in a sample to a whole population. So to check this, she will select a 100 men sample. Excuse me.
Bless you.
Thank you. And so the question that we're trying to answer here is then, so our question is going to be, are men Canadian men in 2020 heavier than in 2015? Okay, this is what we're trying to answer. Now, before I give you the information that was collected for this sample, what I'm going to do is maybe discuss with you what we should, like how we should answer this question. All right. So imagine that I have a given sample, and for that sample, I get an average of X, which is equal to 177. Okay. So if we get a sample average that is 177, then we can say, well, probably, I mean, it's possible that this sample does not represent particularly the population in 2020. She happened to just select men that happen to be lighter than the usual. But chances are that my sample is representative of my population. And so if I get a sample average of 177, chances are that the average for all men is also near 177, and therefore that men have not actually grown heavier in the last 5 years. Okay, could I see a yes for everybody that understands this, please? So if the sample average is 177, the answer is probably not. Are men in 2020 heavier than in 2015? Probably not. Then I have something like if my sample average is, let's say, 178. Okay. Well, if they're just 1 pound, if I have a sample of 100 men and they're just 1 pound heavier than what they were in 2015, well, this could just be explained by the fact that I can expect some variability in my sample averages. Remember, we talked about the fact that the sample average was a random variable, and therefore I should expect some variability in it. So if I get a sample average of 178, it's difficult to say whether there's going to, whether this is due to probability or whether they're actually heavier. But if they're heavier, they don't seem to be too much heavier. And so that means that this might just be a fluke, right? So my answer in this case would most likely also be probably not, right? Probably this difference is not significant enough for me to conclude that men are significantly heavier in 2020. Does this make sense for everybody? Yeah, could I please see a yes for everybody that understands this? 'Cause little by little, we're gonna build on this. Now, remember that we're assuming that our sample is very well chosen, okay? So it's perfectly random. I have no reason to believe that there's any kind of bias. So I'm assuming that my sample is good, okay? And this is, so we're assuming that the sample is good, okay? So what this means, why I want to emphasize this is that if at any point you get results that seem a bit fishy, you should not right away hesitate of the quality of the sample, because for here, we're going to assume that my sample is proper, okay? It's appropriately chosen. It's just a random sample that has been chosen the correct way. All right, so my sample is good. Now, if I get an average in my sample, and I have that my sample average was something like 210. Okay, so I have a sample average that was 210. Then, well, this seems like if I selected a sample and the average in my sample was correctly chosen and I got an average of 210, then chances are that there has been a change over the last 5 years, right? So chances are that there's actually going to be a difference between these. Yes, Sarah.
Okay, I don't know if you're gonna get to this point, but like where's the limit between a difference or not a difference, or do we have to do like finding the confidence interval to then decide?
So we're not going to use the confidence intervals. We're going to use probability though. So that's exactly what I'm getting at. It's difficult to know exactly where to stop, right? Because for a sample average of 210, it's pretty evident that there is a difference, right? Like it's pretty obvious that this is too extreme a result. All right. So if x is equal to 210, then probably I can conclude that men in 2020 are heavier than in 2015. So Valeria, I'm not sure I understand your question. On the chat, you're saying if in your sample you get the same mean as in the 2015, I'm assuming, population, don't you have to do more trials? I don't think so. It just means that it happened to be the same.
I mean, I kind of mean that if you get the same average, like, don't you need to, like, maybe it's just a mistake. Like, maybe it's just by chance.
Maybe it is, but
I don't
there's
know,
no
I was
reason to believe that if you choose
confused.
another sample, you're going to get something different, right? Essentially, here what we're saying is we're
Okay.
going to trust our sample and what it says to us. All right, so if the sample average is 210, then you have like, yes, probably there is a significant difference. But then there are cases that are a little bit more gray. So for example, if I get an average that is equal to 183 pounds, okay? So this is 6 pounds heavier than in 2015, and it is not clear whether this could be due to chance or whether this is not explainable by chance alone, right? So in these cases, it's unclear just by looking at it, right? And so the idea is to say, okay, well, if it is unclear, then how do I make a decision based on data? Because most likely I'm never going to get results that are as extreme as 210 or as close as 177. So how do I determine what is the value that can convince me that the weights have actually increased significantly? All right. Well, to do this, what we're gonna try to do is to, okay, so this is kind of the idea that I want to instill in you, which is that we need to try to determine that boundary that is going to separate the results that will convince me that the mean is larger from the results that will not convince me that the mean is larger, okay? So we're going to assume, let's assume that the mean in 2020 is no different than the mean in 2015. Okay, this is the assumption that we're going to make. And then what we're going to try to do is to say, okay, well, if my data suggests that this is not the case, then I'm going to have data that contradicts this hypothesis, right? So what I'm going to try to show is that this is false. Okay, so I'm going to assume that the two means are the same, and what I'm going to try to show is that my data suggests otherwise. Okay, I'm going to try to show that my data contradicts that assumption. Okay, can I please see a yes for everyone that understands that? So I'm gonna try to, I'm going to see if my data suggests otherwise. To do this, I'm going to start by setting up a level of tolerance. Okay, so we're going to call that a significant level. So let's pick a significance level of 5%. Okay. Now you don't know what a significance level is yet, so I'm going to define what the significance level is now. Here's how to interpret the significance level. I'm going to say that my data contradicts the original assumption. So this is the assumption that I have, right? I'm going to assume that the mean in 2020 is no different than the mean in 2015. What I'm going to try to show is that if that is the case, so assuming that the thing that I highlighted in blue is true, I'm going to conclude that a result cannot be explained by chance alone, if it is in the 5% most unlikely cases. So this seems a little bit puzzling, but essentially what this means is that my significance level of 5% means that I'm going to assume that the means are the same. And based on that, I'm going to say my data contradicts that if my data is very rare under that assumption, right? So if it's very unlikely for me to observe what I observed in my sample, then that means that my sample cannot be explained by chance alone, right? It can't be explained by the distribution that I assume to be true, and therefore that assumption must be false, right? And that 5% is just my level of tolerance. So that means that I'm going to be willing to select a level of 5%, means that if my data is in the 5% most unlikely results, then I can't reasonably explain it by chance alone, and therefore I'm going to have that the original assumption was false. All right. Could I please see a show of hands for everybody that more or less understands this? Okay, I have some people that are not raising their hands, and I want to know what part is, unclear, or what would you like me to re-explain? Okay. All right, so again, what I'm going to do is I'm going to clear everything first. And what I'm going to do in terms of statistics here is that if my result is very unlikely based on the assumption that I made, then that assumption must be wrong, right? So for example, if I assume that all my students are really bad in math and then they get an average of 90%, then that suggests that they're not really bad in math, right? So the fact that they're really bad in math couldn't explain such a high average, and therefore I must refute my original assumption. Does that make sense? That's, I think, maybe a little bit more of a personal example. Makes it a little bit easier to understand. Okay, now keep in mind the significance level is arbitrary. Okay, so it depends on how much evidence you want in order to refute your original assumption. So in this case, for example, I want a significance level of 5%, which means that if I'm in the extreme 5%, that will be enough for me to reject my original hypothesis. But if I have something and I want to make sure to be really, really sure of my conclusion, then I'm going to select a smaller significance level, right? So if I select, for example, a significance level of 1%, that means that I would have to be really extreme to reject the hypothesis. That means I want to be really sure that that rejection of the hypothesis is correct. All right. Sarah, you have a question.
Yeah. Okay, I was gonna type this, but anyways, show me the whole explanation. Okay, maybe I'm just really not understanding any of this, but I still don't get how this is different, say from like the degrees of freedom or like that type of thing. Like isn't or a totally completely different thing. I'm
not sure what you mean.
Like I don't know, choosing like our he's in a mood today. Don't know what's wrong. Anyways, like, I don't know. I thought that when we were looking at that table, like the degrees of freedom we chose, that like depended on how like exactly we wanted to be. So how is this different?
The degrees of freedom only talk about the sample size, because depending on how large your sample size is, then your sample size is going to be more or less representative. Not more or less representative. Depending on how large your sample is, your estimate or your average is going to be more or less variable, and you have to account for that in your parameter, right? So like in x minus x bar minus mu divided by s over like standard deviation of whatever, right? So that part over there tells you that the smaller the sample is, the more variability you should have. And so your distribution for that sample average is going to be slightly different. Okay. Now, because of that, you have a t-distribution instead of a z-distribution. What I'm saying here is completely on the other side. It's just I don't know yet what the distribution is here. I'll talk about that in just a second. But that distribution, so like based on whatever the distribution is, whether that is a t-distribution, whether that is a normal distribution, we're going to try to determine what the most extreme 5% cases are. And once we have that, we'll check if our sample gave us an extreme result or a not extreme result. Okay, so it's the difference between how to choose your distribution and then how to compute things from your distribution. All right, can I see a yes for everybody that's following all of this, please? It's a subtle conversation. Okay, so I will say that I have, yeah, what's up?
Sorry. So like, do we have to pick like 5% or like we can decide what's the range?
Okay, in your projects, you'll be able to decide. In an exam or a homework or anything like that, I will tell you what significance level to use. Okay, but it's always set beforehand, which means it is not something that you adjust in order to make sure that your conclusions work. It's something that you decide beforehand and then you use in order to draw your conclusions.
Okay, thank you.
Yeah. All right, and so now that we have talked about the significance level, we're going to talk about that, about how to use it. Okay, so let me just check that yeah, that's good. So I have my significance level, it's all good. Now, based on my assumption, on this assumption, the assumption that there is no difference between the two means, we are assuming that in 2020, so this is my population in 2020, the population mean, so this is my population mean is 177. Okay, this is for our case in particular, right, based on what we did before, because you know that the mean in 2015 was 177, and therefore, if you're assuming that there's no difference, then you're assuming that in 2020, the average was also 177. Yes, Lori?
Quick question, why did we did the margin?
Oh, because I'm writing on it afterward.
Okay.
Yeah, so eventually I'm going to like draw some steps and like I'm going to label them because I'm showing the logic behind everything, and then afterward it's just going to become a series of steps, but I want you to understand the logic behind all of it. Okay, so we have a population whose mean we are assuming to be 177. From here, what we know is that we selected a sample and it happened to be a sample of size n is equal to 100. And we're going to compute an average and a standard deviation from this sample. Okay? Now, because my sample has more than 30 observations, I can use the central limit theorem, and I can conclude that x bar minus the mean, which is this one over here, divided by s over square root of n, which is 100. This is going to follow a normal distribution with parameters 0 and 1. All right, so now we have the distribution. So we know that this is a normal distribution. This is from what we did in the previous section, from what you have in the homework. I'm going to continue the margin on the next page.
Okay, quick question. Do
Yeah.
I drop margin for the whole page?
Yes,
Okay.
until yeah, it's worth it. Okay, so this follows a normal distribution with parameters 0 and 1, which means that the distribution for x bar minus 177 over s over square root of 100. This distribution is going to be a normal distribution. It's going to look like this. Oops. Where this is 0, and we know that this is like 1, before this is 1, -1, and so on. Now we said we're going to conclude that our result is very unlikely. It is if it is in the most extreme 5%, right? So we're saying because the level of significance is 5%, then we're going to say that my result is very unlikely if it's in the extreme 5%. And for us, the extreme 5%, because we're trying to show that the mean is actually larger, right? So that's what we're trying to determine, whether the mean in 2020 is larger than 177. The extreme 5% is going to be this extreme 5%. Okay, so this is, oops, this is going to be 5%. Now, if you look for that in your table, you'll realize that you did this already last time. The value that separates the top 5% from the bottom 95% is 1.645. Right? I trust that you know what I'm talking about, because this is the normal distribution with parameters 0 and 1. Okay? So that means if for my sample, x bar minus 177 divided by s over square root of 100 is larger than or equal to 1.6, actually strictly larger, than 1.645, then that would mean that my sample gave me a result. My sample gave me a result in the extreme 5%. And so it is unlikely. So it is unlikely to be this high due to chance alone. Okay, now you might realize here that we have not used any data for the sample yet. All that we have done is determine under which conditions we're going to conclude that my sample gave me a given result or another. All right. And so now we can start thinking about our sample. Okay, so actually, x bar is equal to 183. It turns out that for your sample, you found an average of 183 pounds and a standard deviation of I believe 20. No, 22. Okay, so that means that for my sample, x bar minus mu, which is minus 177, divided by 22 over square root of 100, sorry, this I have not replaced yet, s over square root of 100 is equal to 183 minus 177 divided by 22 over 10. Okay, and this is 2.73. Now 2.73 is larger than 1.645. And so that means that my sample gave me too extreme a result to be explained by chance alone, right? So my sample a result in the 5% most extreme. Right? If it's in the most extreme, if it's in the most unlikely result, right? So it's in the 5% that is most unlikely, then I can say that my original assumption was probably not right, right? So I can say that my assumption that the means were the same was not right. Which means that I have some reason to believe that the weights have actually increased. Okay, so I have reason to believe that the weights have indeed increased. Now, is it possible that I made a mistake? Yes, it is possible. It's possible that I made a mistake because it's possible that I just happened to choose a sample that contained a lot of men that were very heavy, right? That's a possibility. It's what happens with random chance. But what I have concluded here is that that is very unlikely, and therefore it is most likely that that's not what happened for me. Most likely what happened for me is not that I happened to choose a sample that was too extreme. Most likely what actually happened is that my sample was indeed coming from a heavier population. Okay. Lori, you had a question?
I don't know. I'm still troubled because if it's 5%, then it means it's really like small. And I don't know, like I feel like what we've been before is like, oh, it's like very small, so it's unlikely. Or I don't know. It's just I still don't understand why. If it's in the little 5%, then oh my god, all of a sudden like something changed. I don't really.
So you're asking why 5%?
Well, not necessarily the 5%, but more like why in this small region, why are we not considering the big region?
Right. Okay. So what this is saying is that if your population had a mean of 177, then from a given sample, you would expect the average to be very close to 177. So it would be somewhere around here, right? So this parameter would be somewhere around here. Sometimes, very unlikely as well, you would have a result that would be very small, right? So if you happen to choose a sample that is just made up of men that are very light, right? Sometimes it's going to be very high, right? But it is unlikely that it is in the top 5%, right? There's only a probability of 0.05 that it is as high or higher than this value of 1.645. That means it's quite unlikely. And that means that if we find such a result, then because it's unlikely that it comes from a population that had a mean of 177, then we can conclude that most likely it does not come from that population. Okay, so it's kind of like saying, you know, this seems fishy. You know, it could happen, but did it really? It's kind of like it's if somebody tells you, I have a coin and I flipped a heads 20 times. You're going to say, like, based on the assumption that it's 50-50, you say that result is very, very unlikely. It's possible, but it is not very likely, which means that possibly your coin is rigged. Right? So you're rejecting the hypothesis that the coin has a 50-50 chance of falling in heads because, well, your result, a result of 20 heads in a row, would be very unlikely, and therefore you have to question the original assumption. Okay. All right. So I'm just going to label everything that we did. Here's where the margin comes into play. These are the steps that we're going to follow. The first thing that we did is we set up what we call a null hypothesis, which is the hypothesis that we're going to try to disprove. Okay, we're going to try to show that this is not the case. In this case, we're trying to show that the mean in 2020 is different or is higher than the mean in 2015. The null hypothesis is that it is the same. So that mu is equal to mu0, which is a comparison value. Okay. Then, so this is for this assumption. Then we're going to see if the data suggests otherwise. Okay. So we're going to try to test what we call an alternative hypothesis. Which is that mu is actually larger than that comparison value. Okay, I'll write all of this again on Monday, but I want you to think about this, okay, and to try to convince yourselves of how this works. Then we pick a significance level of 5%. So what we have picked, pick a significance level, which we call alpha, okay, and in this case, our alpha was equal to 0.05. The fourth thing that we do is try to see, based on the assumption, what the test statistic should be. Okay, so the test statistic is simply the value whose distribution I know. Okay, it's called the test statistic because you're going to be able to compute it from your sample, but it's simply something whose distribution you are able to find. Okay, so this is called, so you're going to state the test statistic and its distribution. In this case, this is our test statistic, and this is its distribution. The fifth thing we're going to do is find what we call a rejection region. Okay, the rejection region is the values for which we will reject that original hypothesis that we made, right? So find a rejection region, the rejection region which in our case was this, right? So the rejection region is simply the thing that tells us whether we're going to reject our hypothesis. The next thing that you're going to do is just find your test statistic for your sample. So that means collect data and find the test statistic. And then from 5 and 6, you can conclude. Okay, and so here our conclusion is based on the rejection region. If I fall in the rejection region, then I reject my original hypothesis, my null hypothesis, whereas if I fall outside of my rejection region, so like in the area that I should expect my values from, then I have that, that's going to be that my null hypothesis is valid. It's a reasonable explanation for my data. Okay, so we'll see exactly how to apply these in more examples, and in the next couple of weeks we're going to do a lot of examples for these, but I would like you to review these notes and try to think about the logic here, okay, because it is kind of a counterintuitive type of problem. So I just want you to think about how it works and why we have to proceed like that. Okay, so instead of showing that a result is very likely, we're trying to show, okay, if I already know something, I'm going to show that my result is very unlikely to come from that, and that will disprove my original hypothesis. Okay, so instead of proving something, which is difficult because you don't really know how to get to that, what we're trying to do is disprove the opposite. Okay, we're trying to disprove that the opposite is true, and that's easier because that means we can assume that that is true, and then we can show that it couldn't be. Okay, that it is very unlikely that it is. All right, so it's essentially like a proof. It's just that the proof is done by contradiction. We're just saying, let's assume that this is true. Now let's prove that it is not. Okay, so that's that for today. If you have any questions, I am willing to take them now. If not, then I'll see you on Monday.